So welcome everybody. I am Lyle Kopnicky. I'm going to be talking to you today about natural deduction. And I have been studying mathematical logic for about a year now, and I thought I'd like to share with you some of the beginnings of it, some things that I've learned that are applicable to functional programming and math in general. There's some handouts going around. It'll help you. If you get one of those, you won't actually need it until we start the exercises. I also wrote on the board up there the Slack channel for this talk. So in there, I have some instructions how you can set up your computer to run a Haskell stack and how to download the repository from GitHub for the code that you will use in this workshop. But we will only be using that code in the last half hour of the workshop. So it's no hurry. And we will be having a break in the middle for about 10 minutes. OK. So natural deduction is a system for doing logical proofs. We're first going to talk about natural deduction, and then I'm going to talk about, and we're going to do some exercises and learn how to do some proofs. And then I'm going to talk about the correspondence between proofs and programs. Take the proofs and turn them into Haskell programs. And then in the last part of the workshop, I'm going to demonstrate to you a proof checker that I wrote in Haskell, and you'll get a chance to make use of it. A natural deduction is a formal system of logical reasoning. It was developed independently by Gerhard Gentzen and Stanisław Jaśkowski, but they use different notations. The notation we're going to be using, I hope I said that correctly for any Polish people here. The notation we're going to be using comes from Gentzen, and it's a tree-like notation. It's the same kind of notation that you would see if you read Haskell papers or papers about type theory. So this will help you get a little more comfortable with that notation. And it was designed because previously people were using something we now call Hilbert systems, and those were a little bit hard to reason in. It's called natural deduction because it felt to mirror more the processes that we use when we think about proofs. So let's talk about what are propositions. A proposition, an example of a proposition is, it is raining, or the ground is wet. So we will use symbols to represent these propositions. We'll use letters. So let's say P stands for it is raining. Q stands for the ground is wet. Then we have logical operators that we can apply to these propositions. That this operator here means not, so not P says it is not raining. And then P and Q, you can think of it as an and because it looks like an A. It is raining and the ground is wet. The next line is P or Q, it is raining or the ground is wet. And then this arrow is an implication. If it is raining, then the ground is wet. And finally, we have these two special symbols for truth and falsity that look like, you might also call them top and bottom. Truth is a proposition that's always true. Falsity is a proposition that's never true. It's sometimes called contradiction. In my proof checker, I called it falsehood for some reason. So I'm going to use, to distinguish between propositions that are atomic, like it is raining, and compound propositions that are made up out of other propositions, I'm going to use different variables to stand for them. So if I use letters P, Q, R, S, those represent atomic propositions. If I use letters A, B, C, D, those represent compound formulas. And I have some examples here. You can see that I can use parentheses to group these logical expressions, formulas. And this not symbol binds tighter than the or, so this means P or not Q. It's as though the not Q were in parentheses. Now, I'm going to introduce the rules of natural deduction, and then we'll see how to use them. So the first rule, the simplest one, is for conjunction, and is also known as conjunction. And conjunction has a rule by which you can introduce it. So if you have a proof of A, if you have a proof of the formula A and you have a proof of the formula B, then you can combine those together to get a proof of A and B. It sounds very trivial, but once you start working through these proofs, you'll see that it's useful. There are also two elimination rules. If you have a formula composed of two formulas with a conjunction, A and B, you can then extract from that a proof of A, or you can extract a proof of B. Here's an example of a proof, and I'm going to walk through this top to bottom, step by step. Let's say we started with this assumption, P and Q. So we know P and Q is correct. From that, can we prove Q and P? What does that sound like to you? Does that ring a bell? Yeah, commutativity. So here's how we're going to prove it. We're going to start out with two copies of P and Q. So one thing about natural deduction is sometimes you need to have multiple copies of a formula, and you're allowed to make as many copies as you want. And in one copy, we're going to use and elimination on the right, that's why there's a sub R, to extract the Q. And in the other copy, we're going to use and elimination left to extract the P. Then in the next step, we're going to apply the and introduction rule. So now this Q is on the left, P is on the right, and we can combine them to get Q and P. So that may seem simple, but it's the beginning of the workshop. So trust me, they can get a lot more complicated than that. But there's an interesting dynamic going on here with elimination and introduction. Introduction brings operators into play. Elimination takes them out of play. It's like you're adding information, and then you're taking information away, extracting it back out. And Bob Harper likes to talk about this as like a conservation of information. You put it in and you take it out.
Why would element U and P is it arbitrary?
What's that?
Like, why you eliminate U and P? Is it arbitrary?
Because that's the strategy that I had to follow in order to make this proof work. As I'll talk about going through the proofs, like try to give you some insight as to like how you can sort of pattern match and say, oh, for that kind of formula, here's how I might approach the proof. So here's another example. This one has a nested formula with parentheses. From the assumption P and Q, we want to prove P and parentheses P and Q. So first, what do we need to do? We need a copy of P by itself. So of course we're going to have to do and elimination left to get the P. And then in the next step, we're going to make use of P and Q again. And we're going to combine it with the P to get P and Q. And you see how I had to put parentheses around this because it's a subformula of this formula.
So you can
Is that
the original expression anytime during one proof?
Yep. Yeah, you can make as many copies of it as you want. It's an assumption behind this proof, so we can use it anywhere we want without any restrictions. So now I'm going to give you an exercise. If you pull out a piece of paper, if you have a pencil, and you may want to join with someone else and try to do this together. We'll take about 5 minutes for this. Given the assumption P and Q, and refer to your natural deduction cheat sheet here, but only look at the conjunction rules. Given the assumption P and Q, can you prove P and P in parentheses and Q? If you have any questions, please ask.
These handouts?
They were going around. Those might be the last ones. And I will go over the solution as well. By the way, there isn't always necessarily just one way to do a proof. There can be multiple ways to do a proof. But for these simple proofs, there tends to be just one obvious way to do it. Not that it's, I don't mean that it's obvious to see how to do it, but.
Sorry, a question. In this implication introduction, what does number 1 mean?
I will get to that later. You won't need that for this exercise. And by the way, one of the things that Gensen was trying to do, he was very interested in trying to make proofs as small as possible. So he realized that if you introduce something and then immediately eliminate it, then there was no point in introducing it. So you can sort of collapse those proofs. So how, yes, question?
This is a question of novice, but elimination, is that modus ponens?
No, modus ponens will be implication elimination. Implication elimination is modus ponens, which we'll get to later. Yes.
Thank you.
You're welcome.
Even more patient. So when you say eliminate left, you actually mean like the left?
Yeah, it really means more like eliminate to the left. We're eliminating the conjunction. We're keeping the left side of it. Yeah. Yeah, yeah. Some people use a 1 there. There's different notations that are used for these things. I chose one that I felt would be easiest to understand. But that's a great question. Yeah, some people use a 1 and 2 instead of left and right.
But it still says
Well, it may just say, usually it just says E. And then I for introduction, which can get a little hard to read sometimes.
I'm appreciating the case of
You're welcome. So how are people doing on that? Anybody feel like they're getting it? Yeah. By the way, if you came in late, I do have the Slack channel listed up there for this class, and in it I've posted some information about setup that you'll need for later. But there will be a break at some point, so don't concern yourself with that too much yet. Okay, I'm going to move on to the solution. So this is the solution that I came up with. So I'm using 3 copies of P and Q here. That was sort of the insight that you needed. I said, well, I need P, and I also need P again. So how do I get P? You may have seen from the previous examples. The way I get it is by doing left elimination on P and Q. And there's no way I can sort of share that and use it somewhere else. I have to repeat that. And that's part of the way that this notation works, this Gensen style of natural deduction. There are other ways to do proofs. And then to get P and P, I take their conjunction. So I've got a P, and I can do conjunction introduction to get P and P. Then I use another copy of P and Q to extract Q and elimination right. And now I can combine those two together to get P and Q. One thing that you might find happens when you're working on these proofs, this happens to me a lot, I use pencil because I often start writing this thing and realize there's not enough space for something and I need to erase things and move it around. I also don't always necessarily write these rules on here, and maybe I fill them in later. I keep them on here because it's going to make things clearer to you, but eventually people just start writing them without the rules because they know what the rules are. Any other questions about that? Okay. So now I'm going to introduce another rule called implication. You could think of it as if-then. Implication is a rule that has both introduction and elimination. There's just one introduction rule and one elimination rule. But this works a little bit differently. Instead of just having one formula up here, we're actually concerned with this entire derivation all the way from here down to here. So somewhere up here we have an A, and we've got a whole bunch of proof steps, and then we ended up with a B. And it actually may be a tree. I mean, with the dot, 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 the ellipsis, it looks linear. But it may actually have a tree structure. We may have multiple copies of A up there. The point is that somewhere up there, A is an assumption, is used as an assumption. And from that, we derive B. So,
Is there significance to the line above A there?
Yeah, I'm about to explain that. Yeah, so when you first write this, you'll have a proof. There won't be any line above A. You'll derive your proof of B. And because you've proven B from A, that allows you to say, well, then A implies B. So that's what this rule says. Since I was able to prove B from A, I can now conclude that A implies B. And when you do that, you write this line above all the A's. Actually, you can write them above whichever A's you want. And that's called canceling the assumption. Because now you've used that assumption to introduce this implication. So you don't get to use that assumption again.
So
you can't cancel it again later.
Can we interpret the nothing over A as being roughly from nothing I can deduce A?
It's really just a notational thing. Some people use a slash through the A, but I find that harder to read.
All right. And I apologize for coming in late. What's the one?
But yeah, you could see that as like nothing gives you A, but.
What is the 1 to the left of the bar?
That's my next. Yeah, great question. Yeah. So the 1 is so that when you do implication introduction, you need to know which assumption was I canceling in order to introduce implication. So I put a label next to it, and since this is the first in my entire proof, this is the very first assumption I've canceled, I call it 1. So I put a 1 next to it. Some people put it on the right. I'm putting it on the left here. I put a 1 next to it, and I also put a 1 next to the assumption I'm canceling. So it's a label that tells me which assumption am I canceling in order to do this introduction. And again, the reason I'm canceling is because it's no longer needed as part of the proof. Before it was an assumption, the proof depended upon that assumption. Now it no longer depends upon that assumption. And the flip side of the coin is elimination, and this is the modus ponens. So if we know that A implies B, and we also know A, then we can conclude B.
So in A implies B, A is in the contravariant position and B is covariant.
Yes?
Is that related to A being below the line and B above the line in the?
Sort of, yeah, because you can kind of see the, this is called the line of inference, this line, and you could, from a meta level, it's like an implication. as
so
well.
that corresponds to taking the external HOM to the internal HOM. With the
Oh, I'm not too familiar with it from the category theory perspective. Yeah.
No, I don't think so. Not in this case.
Okay. Although I know they do logic in category with toposes, but I don't know how that works. Okay, so here's an example. We start with these assumptions that we're not going to cancel. These are assumptions that we're going to stay assumptions for the whole proof. P implies Q, and Q implies R. From that, we prove P implies R. Transitivity, right? Now, I'm not really proving transitivity here. I'm really just proving a specific instance of transitivity for these specific propositions. But that's a fine point.
This is true for all propositions.
It is true for all propositions, but my proof doesn't really say that because it doesn't have a for all in it. But that would be second order logic. So here I have P implies Q, and then I can, you say, well, I don't have P as one of my assumptions. True, I don't have P as one of my assumptions, but I can introduce an assumption. I can say, okay, now I'm going to temporarily assume P, knowing that sometime in the proof I'm going to have to cancel that assumption. And this is a pattern match. You say, well, I know I have P implies Q. The only thing I could do with that is give it a P. So that's how I know that I want to put a P in the proof. The next step is I'm going to use my assumption Q implies R and handily, oh, whoops, I actually went to the next step. So handily, I have that Q. From Q implies R and Q, I can derive R through implication elimination. And then the last step is to cancel that assumption I made, the P. I can't have that in my proof at the end because I'm not allowed to make that assumption. I can only temporarily make that assumption while I'm doing the derivation. Once it's done, it has to be canceled because I'm not allowed to use that. Why? Because I said from assumptions P implies Q and Q implies R, not assuming P, right? So P is just a temporary assumption. I cancel it at the very end. Now it's no longer part of the assumptions behind this proof. And I've introduced P implies R. Okay, here's another example. From no assumptions, we want to prove P implies that Q implies P and Q. And this one is a little bit like currying, if you're familiar with that. So I start out with P and Q as two separate assumptions. Now, wait a second, you said I had no assumptions. Well, why do I have two assumptions? Well, because these are both temporary assumptions, right? I'm temporarily going to assume P, and temporarily assuming Q. At some point later in the proof, they're going to get canceled. So by assuming those, I can introduce conjunction to get P and Q. I can then eliminate, I'm not eliminating P first, I'm actually eliminating Q first, because now I get Q implies P and Q. And I use that label 1 to show that I'm canceling the Q in that implication introduction. And then the last step is now I eliminate the P to get P implies parentheses, Q implies P and Q. Are there any questions about this one?
How do you get the Q implies P and Q? Where does that?
That uses the arrow introduction.
So we have P and Q in this step. At that point in the proof, Q was still an uncanceled assumption. So we're allowed to cancel that and use it to introduce this implication.
Oh, by canceling it.
Yeah, so if I back up here, like I canceled this assumption. It says from Q, I was able to prove P and Q. Therefore, Q implies P and Q.
Oh, I see.
Yeah.
Yeah.
And you said in the script on the left, the 1 is telling us that we are canceling Q first. Is that correct?
Yeah, I mean, it doesn't really matter. It's, well, The labels, as long as the labels are distinct, it's fine. Yeah.
So you could have reversed that and done P first.
Yeah, but then it wouldn't get this result. It would have Q implies P and Q.
Gotcha.
So I wouldn't get the desired result. Yeah. Okay, now I'm going to give you an exercise. Oh, one more thing I want to say about this briefly is that I had no assumptions. This is the first time I had no assumptions. So if I have no assumptions, it's called a tautology. So now from the assumption P, prove that P implies Q implies Q.
Do you have a copy of your handout?
I think I'm fresh out. There is, if you go to the Slack channel, you can download the PDF. Okay, I'm actually going to go ahead and show you the solution. It's a little bit tricky. You know, when the first time I tried to do this one, I started with the wrong assumptions and so on, and that's part of the practice. So the trick here is to start with the assumption that P implies Q. I'm no longer stepping through so you can see the whole thing at once. You start with this assumption that P implies Q, and then what can we do with that? We can give it a P. We can do implication elimination to get Q. And now we have a proof of Q starting from the assumption P implies Q. So what does that let us do? Implication introduction. P implies Q implies Q.
Can I start from Q dot another Q and then I get P plus Q?
Yeah, I think so.
So I just assume P and then.
No, you can't. No, you can't, because there's no way you can prove Q from P.
And you don't need to assume P, you already have it.
You don't have anything that you can use to prove.
Kind of like arbitrary elimination.
We have P, but we can't prove Q from it, so.
You can kind of like make these assumptions in the beginning and then follow it through and see if you're right.
Yeah, yeah. I mean, this is trial and error. You learn after a little while that you see certain patterns, and you can apply certain rules. So I'm trying to give you some examples that show you some of these patterns. Yes?
The left to right ordering of the error elimination, is that significant? Could I have P on the left and then P arrow Q on the right?
I prefer to keep them the same way, but I'm pedantic about it. I've seen other people write the proofs with them on either side. It's sort of like in Haskell, can you call a function and just switch the order of the arguments? Well, Haskell won't be happy about it. But if they have different types, you know, maybe it's okay. Okay, now I'll talk about the opposite of conjunction, which is disjunction or. This one I saved for after the others because it's a bit more complicated. The introduction rules are very simple. So if we have a proof of A, you could even imagine dot, dot, dot above that but we're not actually going to use the rest of the proof. All we care about is that we've done some proof that ends in this formula A. If we're able to prove A, then we can prove A or B. Because if A is true, then A or B is true. Likewise, if we have a proof of B, then we can conclude A or B. So those are called or introduction left, or introduction right, or conjunction introduction left, conjunction introduction right. Yes?
Introduction before, both of the formulas we were talking about were on the top.
Right. So the thing we're introducing is the conjunction.
But where does the B, like in the first one, like intro out, where does the B?
Right. From nowhere. You can just put whatever you want there.
And it's not an assumption, you don't have to cancel it.
It's not an assumption. You don't have to cancel it. That's right. Because I say, you know, if I know it's raining You know, if I know it's raining right now, then I can say, it is raining, or the sun has exploded. You know, like, okay, the sun hasn't exploded, but it doesn't matter because it's raining, right? I can just say whatever I want, like it is raining or whatever, you know, as long as I know that's true. This is really handy that you can kind of introduce whatever you want, whatever formula you want there.
Propositional logic is not linear.
No, it forms a tree. So the complicated bit is this elimination. And the way this works is you have 3 proofs on the top. One of them ends in A or B. And then over here we have 2 proofs. We say, well, in the case that if this were an A, because we don't know if A is true or B is true, maybe both are true, but if A were true, then could we prove C from it? So if B were true, can I prove C from B? So if I can show that I can prove C from A, and I can also prove C from B, then it doesn't matter whether A or B is true, because I can prove C from either of them. Therefore, I can just conclude C.
It is raining, therefore we will have a black hole.
Right. Yeah, so like, I don't know if it's raining, and I don't know if the lights are on in the room. But if I know that it's either raining or the lights are on the room, or both, and they both imply something or other, I'm not going to try to come up with an example, then I can conclude what they both imply.
Yeah. Do you have to be able to conclude C from both A?
Yes. If you can conclude C from A, and you can conclude C from B, and you know A or B, then you could just straight out conclude C and forget about, you know, A or B. Okay, so here's an example. And you don't have to start from when you prove these things, you don't have to necessarily start from the top. You can start from the bottom. Oftentimes you start from the bottom. So in this case, I'm starting with Q or P, because I want to, from P or Q, this is commutativity again. From P or Q, I want to prove Q or P. So in this case, I think, well, in order to prove Q or P, well, I could do it either way. I could say if from P or Q, a rule I can apply to that is or elimination. Or I can think, I need to prove Q or P. How can I do it? And you think, well, one of the rules I could apply to that is that would result in Q or P could be or elimination. I think it's actually easier to start with the P or Q here. So we start with P or Q. And we know we want to prove Q or P. So we can write Q or P at the bottom. Yeah, hopefully we can just prove that directly. And if we're going to put Q or P here, we need it to be here, and we need it to be here. And then the top of this proof has to be P, and the top of this proof has to be Q. And fortunately, these proofs aren't very long. So proving Q or P from P is very simple. Use or introduction right. Proving Q or P from Q is very simple. Use or introduction left.
So it's like any way you can derive something similar from P and Q together, then you can decide that equal with or then you can like derive that from or elimination, right?
Yep. Okay. So another example. This one says if you know P or Q, and you know that P implies R and Q implies S, then you can prove R or S. And I don't want to spend a lot of time on this one, but you notice the same pattern where we have R or S at the bottom, we have P or Q over here. And this has to match that, this has to match that. We have P as an assumption up here that gets canceled. We have Q as an assumption up here that gets canceled, right? And then these aren't canceled. P implies R and Q implies S are not canceled. Why is that? Can anybody tell me? Yeah, because these are assumptions of the entire proof, so I never cancel them. But I can use them. Note that I can use them wherever I feel like. Like over here, it was handy to use P implies R. Over here, it was handy to use Q implies S.
So
Yes?
I notice on here that you never have from A, I can infer A.
Yeah, you don't have from A, I can infer A, because you don't need it. It would just lengthen the proof and wouldn't do anything.
Well, I would assume that I could say from nothing, I can infer A implies A. By canceling the first assumption.
Oh, I thought about that. Ask me later.
Okay.
Yeah.
There's no excluded middle here, right?
No, I'm not. I'm actually only doing intuitionistic logic here today, for time reasons. So there's no excluded middle. Okay, truth and falsity. You can introduce truth from nothing. So here's really what you're talking about. This is not a cancellation line. This is just from out of nowhere, I can introduce truth with no assumptions because it's always true. And there's no elimination for truth. On the flip side, we have falsity. You can eliminate it, but you can't introduce it. You can't introduce falsity because that would be a contradiction in your proof. Is there something wrong? Falsity can occur in your proof, but you can't just produce it out of nowhere. On the other hand, you can eliminate falsity. So if you have falsity, then you can conclude anything you want. This is called the principle of explosion, or ex falso quodlibet. And that means basically all hope is lost. Like once we have a contradiction in our proof, then anything can happen. Anything is fair game. There are proof systems where that's not allowed, but in standard intuitionistic propositional logic, it is. And then we have negation, introduction, and negation elimination. Now, negation is really just a shorthand for A implies falsity. In other words, A leads to a contradiction.
That sounds intuitionistic.
It's also classical. Yeah. It's intuitionistic. It's also classical logic. So if we know something, if we can prove a contradiction from A, then we know A must be false. So an example of that is here, where we have the elimination. So if we know both not A and A, those can't both be true at the same time. So we can conclude falsity. We've arrived at a contradiction in our proof. Those contradict each other. And on the flip side, if from A we can prove falsity, then we can conclude that A is not true. So we conclude not A. And that, again, cancels an assumption. But like I said, it's just a shorthand for A implies falsity. So that's why this looks so similar to the rules. If you compare this to the rules for implication, introduction, and elimination, it looks basically the same. OK. So here's an example from not P or Q. And P, we prove Q. And the way I'll do this is I start with not P as an assumption, a temporary assumption. I have P, which is one of the assumptions of my proof. Those cancel each other out. I get falsity. From falsity, I can conclude anything I want using falsity elimination, so I can conclude Q. Now, that may sound really strange, but I'll explain it from another angle in a second. Over here, I just have Q. Well, but it's an assumption, right? Why is it an assumption? OK, because over here, I'm doing OR elimination, not P or Q. So when I do OR elimination, then I have two proofs. This one has to start with not P and conclude Q. This one has to start with Q and conclude Q. So this starts with Q, concludes Q. This starts with not P, concludes Q. When I do OR elimination, I cancel those assumptions, this one and this one. So the way you can think about this, it seems really weird that I have falsity in the middle of it. The way you can think about it is basically this branch, this case can never happen. Since P is not true, we don't really need to worry about that ever happening. And so this is just sort of like a placeholder to say, yeah, if P were not true, we could conclude Q. But since, or I mean, if P were true, we could conclude Q. But we can conclude, well, P is not true anyway, so it doesn't really matter. Right? On the other hand, if Q is true, we could definitely conclude Q.
So if something's not P or Q and P, that's confusing me. Like P is not true and
These are two separate assumptions, not P or Q, and then P is a separate assumption. I'm not using the conjunction operator there. And it turns out this is actually, if you're curious, this is a different way of writing implication. So this is the same as saying P implies Q. In fact, you could do that in one more step with implication introduction here. You could cancel this P and conclude P implies Q, therefore showing that from this we can deduce P implies Q. And you can actually do it in reverse order too. OK, so now you have an exercise. From the assumption not P or not Q, prove not P and Q. And remember, it's like pretend there are parentheses around not P or there are parentheses around not Q. And don't worry if you don't get all these the first time. You can take the slides. You can go practice these again later. But do please ask questions if you're curious about something.
So if you temporarily assume something twice, can you eliminate those both in one step?
Usually you would.
Okay.
Technically you don't have to. You can, if you have multiple copies of an assumption, you can eliminate 0 or more of them. Well, no, you can't eliminate 0 copies of it. You have to eliminate at least one copy of it. But normally you would eliminate all the copies of it that are in that tree. I can't think of any use for not eliminating them all, but maybe there is.
Then when I'm labeling two copies, I just label it with the same little subscript 3.
Yep, yeah, you would put the same subscript. In my proof checker, that's how you do it. Yep. And it allows you to eliminate just some of them if you want. OK, I'm going to go to the solution. So we have, this one's a bit longer, right? But I have, maybe the trick here is seeing that you can have falsity. This happens a lot in proofs where you have falsity as the thing that you conclude from your OR elimination. So once you've seen it, then you start to say, oh, OK, maybe I can use this as a trick, and maybe it'll come to your mind the next time, right? So I have this assumption, not P or Q, not P or not Q. And so the first thing that comes to my mind is, well, I want a pattern match on that and say, I can use OR elimination. And if I'm going to do that, then I need a proof that starts with not P, and I need another proof that starts with not Q. And what am I going to conclude in those proofs? Well, you might, if you looked at my previous example, you might think, well, I'm going to conclude not P and Q. But unfortunately, there's no way to just get to that step right here. So this is a little bit more complicated. But another hint here is that if you think, well, I need to conclude not P and Q, that you're using not introduction. So you want to start out with the assumption P and Q and show it leads to a contradiction, and then you can conclude not P and Q. So if you put those two hints together, you can think, well, that's why I'm starting out with P and Q, right? So I have my P and Q. I said, what can I do with P and Q? Well, I didn't put all my rules on here, unfortunately. That's and elimination. So I can eliminate, get the P, and that contradicts not P, which gives me contradiction. I can do the similar thing on the other side. P and Q. I can do and elimination to get Q. That contradicts not Q. So I get falsity. Now I have falsity here and falsity here, which allows me to conclude falsity with or elimination. And then from falsity, I can, right. I have the wrong rule here. That's a mistake. That's not falsity elimination. I used negation introduction. I will have to fix that. Yeah, I'm not just saying, I'm not using ex falso. I'm not saying from falsity I can conclude anything here. I'm saying, even though I could use that rule, but that wouldn't get me where I want to go. What I'm saying here is I was assuming P and Q. Now I'm canceling that assumption to conclude not P and Q. So yeah, that is the wrong rule there. It's not introduction.
So you couldn't cancel the P and Q assumptions.
Yeah, that's right. If I used ex falso here, I would still have P and Q uncancelled, which wouldn't get me where I want to go because I want to cancel those.
So it's legit though in not introduction to cancel in your diagram to have as many of these A's at the top that you want as long as you cancel all of them?
Yeah, you don't technically, when you do a cancellation, you don't have to cancel all the copies.
So you can't.
But if you don't, you might run into problems because, yeah, you can cancel them all, and usually you do. Usually if you don't cancel them all, then you'll probably run into a problem where you have an assumption lying around that you don't want to be an assumption of your proof, right? I haven't found a case where I didn't want to cancel them all, but technically you can. So we're going to take a break now.
I guess if you were going to cancel,
we're going to start back.
Introduce one again with or introduction.
In about 8 minutes. Yeah. Yeah, I saw that I had. The question is, how did I decide I needed P and Q up here? It's because, through intuition or having worked with these proofs, I said, well, I know I'm trying to prove not P and Q, and I see that's a pattern. I said, okay, how can I prove not P and Q? Usually the way you can prove a negation is by first assuming the thing you're trying to negate. So I said, I'm going to assume P and Q and see where that goes. What can I do with it? And it turned out I could do something useful with it. So yeah, we're breaking now.
And then you're assuming not P as well. The one again.
I think that's taken from the not Q, just kind of moves that up.
Okay.
But yeah, I'm happy to answer other questions while people were, taking a break, doing whatever they need to do until about 7 minutes from now.
Do you mind saying where the slides are again? The URL for the slides?
On that Slack channel, I posted a URL with a link to the slides. Although I'll have to fix them now because we saw that mistake on this slide.
They're just moving the not P up. You're just extracting it from the not P or not Q.
Well, the rule for or elimination is I have to, from not P, I have to prove something, and from not Q, I have to prove the same thing.
Yeah, so when the not P and not Q up above, those two?
Which? This is not P. Oh, this.
Yeah, where are those coming from?
This not P. So to do or elimination, I have to assume not P and prove something. So here I am assuming not P. And notice that it's canceled with the number 1, which is the same number that's to the left of this OR elimination. It's canceled by the OR elimination.
So why the OR elimination cancel not P?
Because OR elimination, the rule says, if you look at your cheat sheet, the rule says that I have to start with the thing on the left of the OR and prove something. And then I have another proof that starts with the thing on the right of the OR and proves something, right? And then I get to cancel both of those assumptions. I have to cancel both of those assumptions in order to eliminate the OR. And canceling assumptions means that I'm no longer depending upon this assumption in my proof.
What was the correct elimination at the bottom there?
Intro.
Yeah, this one on the bottom is not, that's incorrect. It's not falsity elimination. It's not introduction. Could write it on the slide. Yeah, I can't do that. So that's not intro. It's kind of hard to write.
You're not awake, either not awake or you're not sleeping. You cannot be sleeping and not awake.
Yeah, that's a good example. So you said this could be either you're not awake or you're not sleeping. Yeah.
Same as you're not.
In that case, I guess P is not, Q is not P or something, which isn't always necessarily the case for this, but it is an example, yeah. It's a bit more constrained because P and Q don't have to be negations of each other for this to work.
The negation introduction is just proof by contradiction, right?
No. The term proof by contradiction is maybe used a little bit loosely sometimes, but from what I've seen it defined, it always means it's similar, but it's the opposite. So negation, it's actually similar to negation introduction. So negation introduction starts by assuming A. You show that leads to a contradiction. So now you can conclude not A. The proof by contradiction is the opposite. You start by assuming not A, and then you prove a contradiction. Therefore, you conclude A. That rule is not on your sheet because I didn't want to take time to cover it. It's a rule that belongs to classical propositional logic, but not to intuitionistic propositional logic. It's like the one extra rule.
So could you have taken these steps in kind of the opposite order, where you take P and Q as your first assumption, and basically get P and Q, therefore falsity, from both not P and not Q, and then use OR elimination at the end?
I'm not sure I completely follow the proof, but yeah. Hold on a second, I want to see what time it is. The one on the bottom?
Yeah, the bottom one, sorry.
Okay. You know what's going to be great about this? When I show you my proof checker, you can actually transcribe this into the proof checker and it'll tell you if it's right.
Oh, cool.
It's a good pitch.
That's why I wrote it, because I'm writing these proofs out on paper. And I don't know if I did it right or not, because it's on paper. So now I can put it in the computer. You're missing a, what I call an antecedent. So on this or elimination, there should be 3 things above the line, and you only have 2.
Well, here, this thing.
Ah, right.
Yeah, sorry,
Okay.
the line isn't long enough.
Right.
If you see that, suddenly like have to do like
I think that looks right.
I think it's just like
that looks right.
I did one thing before the other. And
Yeah. Yeah, I think that looks right. I don't have time to fully convince myself, but. Okay, I'm about to get started again. Actually, 1 more minute.
So I think I have an argument about why it doesn't go the other way. So from this one, if you have a function p implies void, then it's only inhabited if p is void, right? So not p only makes sense if p is false, right?
Mm-hmm.
So given this thing, we either have p is empty, and we can do this one, or q, but, and from that we can derive a p implies q, because if p is empty, this is just the trivial function, because empty has no value that it maps to. But going the other way, we have a function from p to q. We can construct a q given a p, but that doesn't entail that we can that p is void or that we can get a q from nothing.
I'm going to have to think about it later.
We can construct one of these from where it goes, but I don't see that we can go the other direction.
Okay, I'm going to have to think more about it later. Sorry, I'll need to get back to this.
Rightly so.
Okay, that concludes our first half, and now we're going to talk about the Curry-Howard correspondence. So this is a concept named after Curry and Howard. A concept that proofs are programs, and also that propositions are types. So what do we mean by that? That means that the propositions that we've looked at correspond to types in certain programming languages, especially in the simply typed lambda calculus in this case. So the kind of logic we were looking at, intuitionistic propositional logic, maps exactly onto the simply typed lambda calculus. But we were going to look at examples from Haskell, since that's close enough. It just has extra stuff in it. And if you take a type in simply typed lambda calculus, you can turn it back into a proposition in intuitionistic propositional logic. Likewise, proofs correspond to programs. So just in the way that a program inhabits a type, so if you have a type, well, let me go to the next slide. If you have a type that has values, we call it inhabited. And if you have a type without values, we call it uninhabited. And you might think, well, how can I have a type without any values in it? Like all types have values, like string and int and so forth. Well, this is just a theoretical type. You can define it in Haskell. It's actually in a library called data void. It doesn't seem very useful at first, but it turns out to be useful when you think of it in terms of this logic.
So is undefined value of type void?
No, undefined is bottom. And this is where, in order to map this onto Curry-Howard, we have to pretend that bottom doesn't exist. So an example of an inhabited type, like I can declare type data P and give it two constructors P1 and P2. With the right language extension, I can say data void and give it no constructors, and it's empty. It's impossible to create a value of it, of that type. So proposition turns out to be equivalent to asserting that a type is inhabited, that it has values. So here's a comparison. This is the propositions are types comparison. We have a proposition. If we have a proposition A, we can come up with a type and call it A, type or a type alias. Same with B. The interesting bit is when we have these logical operators. So A and B corresponds to the product type of A and B. A or B corresponds to either A, B. You can think of it as either one thing or the other. A implies B corresponds to a function from type A to type B. So if you think about those a little bit, we talked about being inhabited. So if A is inhabited, so this pair type of A and B is only inhabited if type A is inhabited and type B is inhabited, because otherwise we can't have both of them. Either A, B is inhabited only if one of these two is inhabited. A implies B is inhabited. Well, it turns out it's always inhabited if A is uninhabited. But if A is inhabited, then B also has to be inhabited, which is the same rule that you follow for implication, actually. And then truth corresponds to the unit type, because it's always inhabited. Yes, there are other types that are always inhabited, but we just need to pick something canonical. And then falsity corresponds to this void type that's uninhabited. Not A, well, we can construct a type alias. We can say not A. Remember we said that not A is just a shorthand for A implies falsity. So likewise, we can say not A means A implies, or a function from A to void. Not A corresponds to a function from A to void. And then if we can write an expression of a particular type and a type checks, then that's a proof that the type is inhabited. Now again, in Haskell we have to, this is except for bottom values, so we have to pretend that exceptions and non-terminating computations don't exist. Now here's the correspondence between proof rules, and, well, these are mostly functions, but in one case it's a value that's not a function. So and introduction corresponds to pairing operator that puts two values together into a pair. And elimination left corresponds to extracting the first thing from that pair, and elimination right corresponds to extracting the second. Implication introduction, that's a little interesting because it actually takes a proof as its argument. So remember at the top of the implication introduction we had a proof. So that proof, the only way we can represent that in Haskell is already as a function. And since we already have a function, there's nothing to do with it. So it's essentially a no-op when you turn it into Haskell. That's why I put ID there. Implication elimination, on the other hand, the modus ponens corresponds to function application. So if we have a function from A to B, we apply it to a value of type A, then we get a value of type B. Or introduction left. Someone asked, how can you get something out of nowhere with or introduction? Well, you can use the left constructor in Haskell. And so if I wrap something in a left, I don't have anything on the right, but I do have a type that represents what's on the right. So the thing that I'm inventing out of nowhere is really just a type, not a value. And it's the opposite, or introduction right introduces the disjunction, the either, through the right constructor. Then or elimination turns out to pretty much be the either function. So people asked about the ordering of, does it matter what order all the things are in on the top? Maybe you can get away with playing around with that, but in Haskell you can't get away with it. So I had to rearrange the arguments to either in order to get it to match up with the or elimination. But either is this function that will take this value, and if it's a left, it applies this function to it. If it's a right, it applies that function to it. This is a function from type A to type C. This is a function from type B to type C. So the result of the whole thing, whether this is a A or a B, you'll end up with a C. And the truth introduction is just, there's no function there. You just put the unit value there. And elimination, or falsity elimination is done using this special function called absurd from data.void. And that's a curious function. I call it the empty function. So if you think about, if you've ever learned about functions as sets of tuples, where you have, or you can think about it as like a mapping from these values to those values, right? So you can think of a mapping as just a set of pairs, mapping the thing from the left of each pair to the thing on the right of each pair, right? Where you're not allowed to have duplicates on the left of each of the pairs. So the empty function is just a set without any of these pairs in it. It doesn't map anything to anything. That's what this absurd function is. So it can never operate on any values. Its input is type void. And since it can never actually be called, you can pretend it returns anything, any type you want. So that's absurd, right?
What's the arity?
The arity?
Yeah.
It takes one argument of type void and it returns an argument of type A. It's polymorphic. Not introduction is like implication introduction. So it's a no-op. We have a proof, and we already have our proof. And elimination is like implication elimination. We have some negated type, like not A, or also known as A implies void, or A to void. We apply that function application to something of type A, and we get something of type void, right? Of course, you can never actually run that program, right? Because you can't get anything of type void. So here's an example. I'm going to give examples for each of the types of operators we talked about before. So this is a proof that we saw before. From P and Q, I get Q and P. And the type is pair of Q and P. From pair of Q and P to pair of, from pair of P and Q to pair of Q and P. And you can derive that from your cheat sheet, Curry-Howard cheat sheet. And then the proof, the proof turns into a program, which is just a function. It's a function that takes this assumption. Remember, we had an assumption underlying our entire proof, P and Q. Well, that becomes an argument to our function. So I'm using the variable PQ to stand for this thing on the left. It's a pair. And then we do the and elimination right. That's second applied to PQ. The and elimination left is first applied to PQ. And then we pair them together, which is and introduction. And then I can simplify that proof a little bit by using pattern matching. It's equivalent to this. I've just simplified it, so I'm pattern matching on the pair of P and Q and returning Q and P. Then it becomes really obvious what we're doing of swapping them around. Here's another one for implication, the transitivity of implication. If we have a function from P to Q and a function from Q to R, then we can derive a function from P to R. How do we do that? Well, we take these as arguments. We take the function p implies q, from p to q as an argument, the function from q to r as an argument, and we return another function, a function from p to r. What does it look like? Well, that takes p, and what are you going to do with p? Well, you're going to apply this function from q to r to it to get r. I'm sorry, you're going to apply the function from p to q to get q, something of type q. And then you're going to apply the function from q to r to get something of type r. And so there you go.
The assumption elimination there is marking that as being a variable under the lambda, and then at the top, and then the place where it's used is saying it's a lambda abstracting that this is the value of the lambda.
Yeah, when I make an assumption, that's a lambda. And then what I produce, the type I produce as a result of the lambda is down here. So I've assumed p, I've produced an r. So I have lambda p, and it produces something of type r, right?
Is there a name for that?
What's that?
Can you call that? Is there a name for that?
Well, this is an instance of transitivity.
Or composition.
Composition of functions, yeah. Yeah, function composition. But these are concrete types, right? These are not type variables. So this doesn't work for every type. It just works for these specific types. If you want to work for every type, then that's second order logic.
Well, you can do equational logic, right? And that works for every type because it's almost got an implicit for all. As long as you're not using the existential, then you can treat these as
you can. I'm being pedantic here. Okay. So this is another one we looked at with OR elimination. And again, you'll see the OR elimination corresponds to an either. And rather than writing that lambda that rearranges all the arguments, I just rearrange them myself here. We start out with p or q here, which corresponds to either pq. That's our argument to the lambda. And then the right-hand side produces something of type either qp. And either takes these two functions. One is a proof from p to either qp, right? Oh wait, it's not a proof, it's a program. Same thing. This program is like a proof from q to either qp. And then I can reduce the entire thing to simplify this a little bit to just proof 3 equals either right, left. You can verify that yourself later.
Is there a natural deduction equivalent to the simplified Haskell form?
A natural deduction equivalent to the simplified. No, I don't think so.
There should be.
Well,
I mean, because it's obviously legal.
I mean, those two Haskell programs are equivalent, so it's equivalent. They're both equivalent to the natural deduction proof, but.
There would be a way to make the natural deduction notation similarly abbreviated.
Yeah, you could kind of see it that way. I mean, this is either, this is right, this is left. There you go. Either right, left. Here's either right and left. And our last proof is that from not p or q, we can get, and p, we can get q. And I'm not going to take we're running a little low on time, so I'm not going to go over this one now. But if you look at the slides later, you can follow that one. You won't need it for the exercise, which you're about to do. So turn this proof that we did earlier, we saw the solution, turn that into a Haskell function using your natural deduction cheat sheet. And if it helps, you can think of this, remember this tree is like an expression tree in Haskell, where the top level of the expression is actually at the bottom of this proof. And the interior, the most nested things in the expression are the things at the top of the proof. Except, I guess, if they're assumptions, then they're lambda. That would go at the top. I'm going to move on to the solution. So,
well, we don't know if it will show, right?
If we have and introduction at the bottom of this proof, so that's going to go on this outermost level of this expression. So we have a pairing of two things. And then inside that pairing is another and introduction, which is another pairing. The piece on the right is and elimination right, so that's second. And on the left we have two copies of and elimination left. So there's two, first PQ and first PQ. Now, of course, in Haskell, you would share those, say let or something, but.
Can you also share those while doing natural deduction? Because it's like you start off with D and
not with this notation,
okay.
No.
Twice, right?
Yep. There are other notations where you can do that, like Fitch style notation. So then I've simplified it to this with pattern matching. And I wrote the type on here so you can verify that by Curry how that matches the thing we're proving. From P and Q, we're proving P and P and Q. So now comes to the final part of the presentation and workshop, where I'm going to show you my Haskell proof verifier. And as an exercise, you're going to take any one of the proofs that you've done in this class, and you will enter it into the verifier, and hopefully it will be correct. Then you can introduce an error into it and see that it comes up with an error message telling you it's not correct. So let's see. So I will get this off the screen. And this way. Now I'm going to share some code with you. Have people had a chance to download any of this code? Okay. If you haven't, then I have instructions in that Slack channel. It's Haskell code, and there's a Git repo. Don't know how to do that, but maybe we could turn the lights off.
Yeah. Go to accessibility and switch the colors.
Okay. I don't know how to do that.
I just meant the global.
Yeah. Oh, I see. Okay, so this is defined, first of all, as a library. And then I have a main program here. There will be future evolution of this where you can just import it as a library. But for now, it's just a main program calling a library. And the way I represent these proofs are using Haskell data structures, abstract algebraic data types. So formula, first of all, I need to tell you that this is not just propositional logic. This is actually classical first order logic. So there are more rules here than you have learned so far. So you can ignore those for now. So we have truth, falsity, I call it falsehood here. We have this constructor for and. We have a constructor for or, colon, pipe, colon. Construction for implication. This one's by implication. It really is just two implications anded together. Technically, there are separate rules for that, but they really reduce to the other rules. We have not, negation. And you can ignore the rest of them except this one is kind of relevant. So rel. Turns out that when we use one of these propositional variables like p or q, then technically, to make this compatible with first order logic, we have to pretend that those propositional variables are actually unary relations. So a relation is something that defines a relationship between one or more, or zero or more values, right? So actually, it's not a unary relation; it's a zero-ary. Yeah, nullary relation. Yeah, sorry. So like, you could say greater than is a relation between, if you have A is greater than B, then it's a relation between A and B. Well, these are relations that don't have any arguments at all. They're just true or they're false. But there's a shorthand for writing that. You can say pvar and give it pvar, and then you just give it a string, and that gives you one of these nullary relations. Term you can ignore because that's for first order logic. Sequent. Remember how when I showed you these proofs, we had a set of assumptions, and then we had a conclusion for the proof? Well, that's what this sequent describes. So sequent is your set of assumptions, and then this is the conclusion of the entire proof. So when you check your proof, if it's correct, it will return one of these sequents. That's really all you need to see in this library, unless you're curious about how it all works. But I'm not going to go into that. Now in main.hs, right now I have a bunch of examples in here. Some of these are first order logic, some of these are propositional logic. I froze this code a while back so I could work on the presentation, so it's not perfectly, I don't just have all the examples from the presentation. But there is at least one example in here which is exactly one that we saw in the presentation. Oh, there is something else I need to show you in the library. The way we construct inferences, which is down here. Oh, and rules. So these are all the proof rules. Truth, introduction, false elimination, introduction, etc. Plus, you don't care about any of the ones kind of below this point. And some of them have a label. Well, the label is really just an integer. And remember that when we canceled an assumption, we had a label. So remember how we had a label to the left of the line where the proof rule was, but we also had a label to the left of the line canceling the assumption. So these are proof rules, and they have to have a label because the ones that have a label are the ones that cancel assumptions. Then we have a derivation. A derivation is our proof. A derivation can be one of two things. Either it's an assumption or it's an inference. An assumption is either canceled or it's not. So assumption has a formula, and it has a cancellation label that's a maybe label. So guess what? If it's nothing, it's not canceled. If it's just some integer, then it's canceled, and that's our label. So the way we will write these is sort of out of whole cloth. Like once you've written your entire proof out, you've canceled all your assumptions, you've got your numbers on there, then you go transcribe that thing directly into this proof checker. An inference represents one of those lines that has a proof rule on it. An inference has antecedents. Those are all the things above the line. So every one of the derivations above the line, it's an entire proof that leads to the formula that's just above the line. Every one of those calls an antecedent. And then the proof has a conclusion as well. So it's a tree structure, just like we saw tree structure with the proofs. You could take two derivations, or a single derivation, or three derivations, and you can put them together using the appropriate proof rule to get a new derivation. And of course, the line of inference has to have a proof rule associated with it. So this structure gives you a little bit of flexibility. You can definitely make mistakes. This is not like Agda or Idris or something like that, where I'm not using phantom types. I'm not making sure that you do it all correctly, because I don't want the errors to come from the type system in Haskell. I want you to be able to take that proof that you wrote on paper and transcribe it one-to-one into this notation, into this data structure. And then you run this verify function. It's called verify. And then it will tell you if it's correct or not. So the verify function takes a derivation and returns it either verification error or sequent. Verification error is just a string or text. So if it fails, you get an error message. If it succeeds, then you get the sequent. So let's look at main.hs. The ones that have pvar in them are the ones that are going to be propositional logic. So this one, it may look a little complicated right now. And one of my future goals with this proof checker is to make a simpler DSL that will generate this data structure rather than having to write it out longhand. But I have not had time to do that yet. But if you keep up with the repo, I will add that in the future. I think at this point I'd rather do it myself. But in the future, yeah, once I get to a certain point, I'll accept pull requests. But I still have stuff I want to do myself. So fortunately, the syntax highlighting helps us a little bit here, because we can see where the strings are, right? So if you squint at this a little bit, you say, at the top we have A and B, and from that we derive A. How do we do that? From and elimination left, right? So and elimination left is our rule. Then from A, we can, well, can we? I don't know. Is this proof correct or not? So from A, we then derive A and B implies A.
Yeah, you can introduce anything to the left and there.
Oh yeah, that's fine, because we had A and B up here as an assumption. Yep. So we introduce it on the left, and from A and B we had concluded A, so we can introduce implication. So that's correct. And that one's first order logic. This curry derivation is one of the ones we saw as an example. where we start with two assumptions, A and B. We derive A and B. From that, we derive B implies A and B by implication introduction, and then we have another implication introduction to get B implies A and B. If you look back at the slides, you'll see that one in there. So don't get too upset if you don't follow this exactly right now, because what you're going to do for an exercise is take any of the proofs that we saw in class. If you worked out an example on your own, I can go back and show a slide if that helps for some particular proof, and then transcribe it into here. And what you're going to do is go up to main, and you see how this is calling. It's calling a bunch of things. You can just comment them all out. and you're going to write some proof, and then you're going to print the results. You're going to say print $verify, my proof, and then below you're going to say my proof : derivation. Well, you don't have to write it down there. You can write it anywhere you want. So let's write it here so you can still see the other bit. So my proof : derivation. My proof equals what? I mean, you fill it in. But you can follow these examples. Don't follow the ones that say var and var. Follow an example that has pvar in it. And then if you need to see what the notation is, you can either look at an example here, or you can look in proof.hs and see the definition of the data structure. Does everyone understand what we're trying to do? Does anyone need me to put up a slide with a proof?
Yeah, you put up a slide with a proof.
Sure. In that case, I will have to. Oh, one other thing I want to show you is actually running the proof verifier. I'm actually going to take out my changes here. So you can do stack run, and if it needs to build it, it will build it. And then this is a bit verbose because I have a whole bunch of things I'm running here.
I don't have a stack run. There's auxiliary command not found in part.
Huh. You don't have stack run, huh?
I have stack, but apparently stack dash run is a...
Not stack dash run, it's stack space run.
Yeah, when I type stack space run, it says auxiliary command not found in part, stack dash run.
Huh. You might have an old version of stack.
Yeah, my version stack run.
I have what, version 171, is that correct? Stack dash version.
Yeah, that is a bit old. I mean, I think they came out with 2 now, but I think I have version 1.9. You can do stack upgrade, and it will upgrade to the new version.
You can also just start a GHCI in
Yeah.
the project.
Yeah, you could do stack GHCI.
I like that, stack run.
Yeah. And then run main. There you go. Good point.
It's stack run and stack run main.
No. If stack run works, then it's just stack run. If that doesn't work, then you can do stack GHCI, and when the prompt comes up, type main. But you see how some of these are errors and some of these are successful. And it gave error messages that describe what went wrong. So I'm going to put up a slide with a proof. Oh, maybe I can open the, might be easier if I just open it in Preview or something, or Adobe. No, I don't actually want to open that one. All right, I'll do it the other way. Let's run it this way. All right, turn off mirroring. So look at that. Oops. There's one, the last one you looked at.
I have a question about the rules that are available.
Sure.
I see not intro, but I don't see not elimination.
Oh, really?
Is it just rename something else, or is it not there?
Elimination's on the lower right-hand side. It's right here.
I'm not talking about in the Haskell, like the proof system that we're working with right now.
Yeah, I'm looking for that.
Not elimination is dollar.
I know.
No. He means in the proof verifier.
Oh, I'm sorry.
Did I forget one? You said you saw we were missing which one?
Not elimination.
Right. Yeah, I think we are missing it. Good catch. Yeah, sorry about missing not elimination. If you tweak your proof a little bit, you could still prove it using implication elimination. But maybe I could add it right now while you're doing that. How are people doing with that? Have you managed to code it up? I mean, I tried to follow this pattern of indentation that helped me keep track of things, because if I didn't do that, I got confused about the data structure. We only have about 5 minutes left. So I'm going to show you just a conclusion slide, and then you can keep working on it. I'll say a few minutes after if you have any more questions. Let's see. My conclusion is, for further study, here are some books that I found useful on the topic. I have been leading a study group, and we went through that entire book, Logic and Proof, which is available online. It's related to the lien prover. So there's a theorem prover called lien, and it shows you how to do natural deduction for propositional logic and first order logic. And it also shows you how to do the same kind of proofs in the lien theorem prover, which, if you haven't heard about it, it's similar to something like AGDA. And a great book, which is or like a paper book, Mathematical Logic by Chiswell and Hodges. They have great explanations, and they're very precise and careful in how they describe things. I've actually done some pull requests to Logic and Proof to fix some errors. So. And then another one that I found later is there's something called the Open Logic Project, and they have several books on logic. The first one is called Sets, Logic, and Computation, and you can download this for free. It's an open source project that you can contribute to. And that seems like a really good resource as well. So any other questions? Otherwise, we can turn the lights on. I can walk around and help people.
So in your repo, you're aiming to do first order intuitionistic logic?
No, in my repo, I'm doing first order classical logic.
Lyle, is it possible to weaken slightly the rules that you have when you do
Sorry, what was the question?
So you implemented classical first order logic.
Yeah.
As I recall, there's one way to set it up, there's some differences in the rules between intuitionistic and classical logic. There's some things that are missing in intuitionistic logic.
Yeah, it's mainly that rule of, yeah, there are various ways to formulate it. One is the law of excluded middle, another is double negation elimination, and another is proof by contradiction, which is when you assume that something's false, show that leads to a contradiction, therefore conclude the original thing was actually true. Those are all, any of those rules leads, if you add them, any one of those rules, then you get classical logic.
So can you just do a small tweak to what you've done there, and you have intuitionistic?
Sure, I just remove the rule. It's actually another name for it, proof by contradiction, reductio ad absurdum.
Right.
Yeah.
Sounds so much more sophisticated.
Yeah, so it's actually in the proof verifier, it's RAA. Yeah. You assume something's, you assume not P, show that leads to a contradiction, then conclude P. And the reason that's not admitted in intuitionistic logic is because in intuitionistic logic, also called constructive logic, people like to have examples of everything. They say, well, if I'm going to prove something, then I need an example of it.
Another way to look at that, I just studied a couple days ago, is I think it's called Programming Foundations. It's a Programming Language Foundations added by Phil Lyle.
Oh, cool.
It's an online book. It's really good. It's got
Okay, good. Put it in the Slack channel. All right. Okay. Yeah, that's it. Thanks, folks. Like I said, if you